Hi everyone, I'm Yifei, a PhD student from UCD. Today, my topic is determination of road profile using multiply passing vehicles measurements. There are four sections in my presentation. Firstly, introduction, direct solution of profile calculation, vehicle fleet monitoring concept, and finally, conclusions. As we all know that over time, roads often become damaged due to vehicle overloading and environmental efforts. For example, the air pollution, this damage may impact the safe running of the transportation network, and consequently, road monitoring is an important area of research. Visual inspection that requires large numbers of inspectors and significant cost. So recently, the indirect or drive-by method is popular. This method using passing vehicles to measure dynamic response, such as extrusions. It has a number of advantages. It is easy to operate, efficient, and economy. In previous research, the road profiles are back calculated from vehicle-mounted sensor data. For example, the extrusions using a very complicated optimization produce. This method involves finding the profile elevations that give a best fit to the measured extrusions data. Today, I will introduce a new direct integration method. This method is much more efficient than optimization method and allows the calculations to be finished in a very short time. I used sprung mass and half-car model in my research. Also, I used Newmark beta integration method to solve the dynamic equation. There are two problems in my calculation, the forward problem and inverse problem. For forward problem, we know the vehicle properties and the profile to calculate the extrusions of the vehicle. For the inverse problem, we know the extrusions and using these extrusions to back calculate the profile. So I used the measured extrusions from the forward problem to back calculate the profile. The result is shown in this figure. We can see that the calculated profile, the blue one, is same as the true profile. In the previous section, that road profiles can be found if we know the vehicle extrusions and vehicle properties. So vehicle fleet monitoring concept is introduced to calculate profiles from vehicle extrusions if we don't know the vehicle properties. For a single vehicle, either the profile or vehicle properties can be found, but not both. But all vehicles in a fleet are subject to the same profile. We can use this feature to find the profile. Here, the direct integration method and the cross entropy, the CE optimization method are used together to solve this problem. This concept is shown in this flowchart. Firstly, we know the exertions response to n different vehicles. Firstly, we generate 300 trail properties for each vehicle and calculate the profile each using direct integration approach. Then we calculate the mean profile of each trail. And then we calculate the objective function of each trail. It is the difference between the profile of each vehicle and the mean profile of each trail. Then the result, if not good, we will identify the top best 10% of the trail properties that give the lowest objective function values are identified for each vehicle. Then we calculate the mean and standard deviation of elicit properties for each vehicle. Then we repeat generate neutral properties using mean and standard deviation and repeat this flow. Finally, we will get the true profile. For sprung mass model, the results show this figure. You can see that the result is good. The black line is the true profile, and dashed line are different calculated profile from different vehicles. The calculated profiles are same as the true profile, but this is the calculated vehicle properties. There's a big difference between the true mass and calculated mass and the true stiffness and the calculated stiffness. But what we found that we can find the good ratio is mean the mass divided by the stiffness. In this column, it is true ratio, and if this column is the calculated ratio, we can see they are very close to each other. Also, I use the half-car model. There are 12 parameters in the half-car model. This is the profile results. The blue line is the true profile, and dashed line are calculated profiles. They're also same as the true profiles. Also, we have the same situation in vehicle parameters. We cannot get the actual vehicle parameters, but we can find the same ratio. Here, the ratio is the other properties divided by the mass, the sprung mass. For example, for the first vehicle, this column is the calculated ratio, and the right column is the true ratio. They are very close to the true value. This is fourth, fifth, and sixth vehicles. So, in conclusion, this profile calculation method is good and have the same result as other methods. Also, using several vehicles, the profiles can be calculated if we don't know the vehicle properties. Also, the vehicle parameters ratios could be calculated. Thanks.